Doing stoichiometry with concentrations involves using the molarities that were given along with the volumes in order to find moles. Everything else is going to work exactly the same. So this is a lot of what we've already done. We should be able to find limiting reactants. We should be able to find the amount of products. So in this case, we're going to start with 20 milliliters of 0.1 molar AgNO3, and we're going to have a solution of 0.05 molar sodium chloride added. Let's look at this reaction. So to start with, I'm going to have AgNO3, N, not M, plus NaCl. This is a common reaction that we've already looked at before, so what is it going to create? What does this reaction create on the other side? Well, NaCl plus AgNO3, anything attached to a nitrate, anything attached to a sodium, always going to be solid. However, AgCl is not soluble. So the outcome of our reaction is going to be AgCl. Very nice. What is going to be our balanced reaction? Well, all of these have a 1-to-1 ratio. Look at these. These are +1 - 1. This is +1 - 1. So we don't actually have any balancing that we have to do. So this is already balanced. So we've written out the complete equation, balanced it. How many moles of AgNO3 are present for the reaction? So AgNO3, how many moles are there? Well, we're told 20 milliliters, so a volume of 20 milliliters, and it's a 0.1 molar solution, so 0.1 molar. How many moles are there? Well, we find the number of moles by taking our molarity, 0.1, because that's going to be moles per liter, and multiplying it by our volume. Our volume needs to be in liters. How do we go from milliliters to liters? It's going to be 1, 2, 3. So it's going to be 0.02 liters. That'll cancel out our volume, and we'll be left with just moles. So we're going to take 0.1 times 0.02. 0.1 times 0.02. That will give me 0.002. So, moles of silver nitrate to start with. Let's write this in another color, keep track of it a little better. It's going to be 0.002 moles. All right. Next question. What is the solid precipitating? Well, silver chloride. How many milliliters of NaCl will be needed to reach equivalence? Now, equivalence is a fancier term that just means the completion of the reaction. Some reactions don't use up everything, and so they reach an equivalent point. But we haven't studied that. So wherever you see equivalence, just think completion. So how much NaCl will be needed to complete this reaction? Well, I know that this is a 1-to-1 ratio, so I'm going to need the same number of moles of sodium chloride as I have of silver nitrate. So I'm going to need, let's just make a little dividing point there, 0.002 moles. And I know I have a solution that contains 0.05 molar. So now to find my volume, I'm going to start with my number of moles. So 0.002 moles. And then I want to get volume, so I need my moles on bottom, liters on top. And this is 0.05 moles per 1 liter, and that will leave me with liters, because the moles will cancel out. So 0.002 divided by 0.05. How many liters is that? And that gives me 40 milliliters. So my concentration is half, so my volume's got to be double. That should make pretty good sense. So 40 milliliters. It's going to be 40 milliliters of NaCl. Okay? What else do I need to figure out? milliliters. What is the concentration of each ion in solution at equivalence? So when this completes, what is the concentration of each ion? Well, what is an ion again? Well, all of these are ions. It's an ion, that's an ion, there's an ion, and there's an ion. So what is the concentration of those ions? Well, each of them is 1. So the concentration of those ions is going to be equal to the concentration of each of these molecules in general. So the way I think about that is I go, okay, well, I've added 20 milliliters to 40 milliliters. So what is my total volume on the other side? Because these are all going to be mixed together, right? It's going to be 60 milliliters. 60 milliliters. Now I need to keep in mind, this right here, this is a solid. So that is not going to be dissolved in the solution. I'm not going to have a solution of AgCl. If anything, I would need to figure out the grams of silver chloride that fell out of the solution. But I am going to have sodium nitrate suspended in the solution. I'm going to have a concentration of sodium nitrate based on 60 milliliters. How many moles of sodium nitrate am I going to have? Well, all of this is 1-to-1. So I could go through and do the math and say 0.002 moles of NaCl, convert it for every 1 mole of NaCl. I'm going to have 1 mole of NaNO3, and then I would find out that I'm going to have 0.002 moles of NaNO3. I could do the math. Or I could just recognize that a 1-to-1 ratio is just going to carry over. Okay. So we're looking for the concentration of each of these ions. The way we write that in chemistry is we put little brackets around that. Na. This is so that if I needed to use the concentration of Na in some kind of equation, it's really easy to just put the brackets around it, and everybody knows that this means the concentration. So I would take a number like molarity here, and I would be able to use that in an equation of some kind. So that's just how we notate that. So when you see these brackets, what you should think is concentration of whatever's inside the brackets. So Na inside brackets is concentration of sodium. So I'm going to do the same thing with the NO3. To be officially official, let's go ahead and put our ionic charges there. So I've got sodium ions and nitrate ions. What is the concentration of each of these? Concentration of Na, well, there's going to be 0.002 moles of sodium ions in there, and it's going to be in a volume of 60 milliliters. So let's convert that into liters. So 0.06 liters, and that'll tell me the concentration that I have. So 0.002 divided by 0.06 gives me 33. Oh, that's why. 0.002 divided by 0.06. There we go. So I should get 0.033 molar. And then what's it going to be down here? Well, I'm still going to have 0.002 moles divided by the same volume. So it's going to be the same molarity. All right. So there are my concentrations. Finally, draw a picture of the beaker at equivalence. So if I wanted to draw a picture of this beaker, what I would do is just make a picture of a beaker right off the bat. I'm going to make a nice fat beaker so I can actually fit my drawings in it. All of my silver chloride sank to the bottom and became a solid. So that's how we'll represent that. So we've got all of our silver chloride hanging out at the bottom here. But still floating in that solution are my Na NO3 ions. So those are still floating inside the water. So that's my drawing. All right, let's look at number 4 together. In this one, we've got calcium chloride being added to sodium phosphate. How much do we have of each? Well, we've got 50 milliliters of a 0.2 molar solution. And this is added to 50 milliliters of 0.4 molar Na3PO4. This is going to form a white solid at the bottom of the solution, and we're first asked to write the complete balanced equation. So the complete balanced equation, this is just going to be a single exchange. So I've got, a double replacement reaction. So I've got sodium, chlorine are going to get together, NaCl, plus, and then calcium and phosphate. So it's going to be Ca3PO4 2. In order to balance this, first let's balance the calcium. There's 3 here, so let's put a 3 over here. Let's use a different color for that, just to make it super obvious. So 3 calciums, put a 3 over here. 2 phosphates, let's put a 2 right here. Let's see, 3 times 2, that's 6 chlorines. 2 times 3, that's 6 sodiums. So I can put a 6 right here, and everything's balanced. Perfect. So of these two, what do we think is going to be the precipitate in this reaction? Sodium chloride is, well, it's got sodium in it, and sodium's always going to be soluble. So this whole thing is going to be soluble. So this must be our precipitate. So let's label that. Let's give that a little S for solid. So that's in the solid phase. So the rest of this is an aqueous solution. So we can move on now. Which reactant is the limiting reactant? All right. So to do that, we're going to have to actually do the stoichiometry here. And our first step is going to be to find the moles of each of these. To find those moles, we're going to go hunting for moles. We're going to take our molarity. So let's start with calcium chloride. We're going to take 0.2 moles per liter and multiply it by our volume. Our volume here is 50 milliliters. Converting that into liters, I'm going to move the decimal place, 1, 2, 3. It's going to be 0.05 liters. Liters cancels out, leaving me with moles. So 0.2 times 0.05, let's break out our calculator. 0.2 times 0.05, and that gives me 10 e to the negative 3. So that's going to be 0.01 mole. Okay? Now let's do that one. 0.4 molar moles per liter times, there we go, 0.4 moles per liter times 50 milliliters. So that's going to be, again, 0.05 liters. Liters cancel out. So I can do 0.4 times 0.05. Wouldn't you know it? Oh. Wrong. 20. So 0.02 moles. There we go. All right. Should get rid of that glare. So what's our next step? We found our moles. We need to figure out our limiting reactant. So I've got 0.02 moles of this, 0.01 moles of this. I can already see, because it takes 2 moles of this for every time this reaction proceeds, and that's already a larger number. This calcium chloride is going to end up being my limiting reactant. Let's prove that. So I've got 0.01 moles CaCl2 times And let's go to Ca3PO4 because it's a 1. So I need to take 3 moles CaCl2 to 1 mole of Ca3PO4, 2. What'll that get me? 0.01 divided by 3 gets me 0.003. Okay, so now let's take this one. So let's go 0.02 moles Na3PO4 times 2 moles Na3PO4 for every 1 mole Ca3PO4, 2. So that's 0.02 divided by 2, so that's going to be 0.01. So we can see, yes, our limiting reactant is going to be the calcium chloride. So what are we going to be left with? We're going to get 0.003 moles of calcium phosphate. So let's go ahead and figure out how many moles we're going to have of sodium chloride. So I'm sure we're going to need that later. So we're going to start with the same math, 0.01 moles of calcium chloride times, for every 3 moles CaCl2, we're going to get 6 moles NaCl. What is that? 0.01 times 6 divided by 3 is going to be 0.02 NaCl. All right. What's the next thing we need to figure out? What is the solid precipitating? Well, we already figured that out. It's going to be the calcium phosphate. Draw a picture of the beaker. So show particle proportionality. Ooh, what does that mean? Well, if I draw a picture of this beaker, I'm going to draw a nice fat beaker so that I can actually see everything inside of it. I mean a fat beaker. All right, really big beaker here. So this is going to be a solid precipitate on the bottom of the beaker. So I'm just going to put Ca3PO4, 2, and just cover that up. Okay, great. That's all there is to it. I'm going to have sodium chloride, so I'm going to have some Na plus Cl minus, Na plus Cl minus, just floating around in there. And then I'm going to have some leftover Na3PO4. So for each one of these left over, I'm going to have 3 Nas and 1 PO4. That's what we mean. When we say show particle proportionality, what we're saying is if I've got some of this dissolved in here, for every one of these, I'm going to have 3 of these. All right. So what's the last thing? What is the concentration of the PO4 ions in the solution? What is the concentration left over at the end? So we need to figure out how much of this is left. How much of this reacted with this? So let's go ahead and determine that, and then we'll come back and we'll figure out how many moles per liter we've got. So determining the moles of this that are left over, my first step is to figure out how many moles got used up. So this is my limiting reactant. So I've got 0.01 moles of CaCl2, and I'm just going to figure out how many moles of this was used by doing that regular proportionality. So for every 3 moles of CaCl2, I'm going to use 2 moles Na3PO4. Let's go ahead and do that. 0.01 times 2 divided by 3 gives me, it's going to be 0.006. So that's how many moles of this got used up. And I started with 0.02. So if I want to figure out how many are left, I'm going to take 0.02 moles minus 0.006 moles. What will that give me? 0.14. So I've got left over, let's put this over here, 0.014 moles of Na3PO4. Now, when we looked at the beaker, we saw that our proportionality of this was that for each one of these that's dissolved in that beaker, there's going to be one phosphate ion. So just to help us understand what it looks like when we have different numbers of this, we're going to find the concentration of both the phosphate and the sodium, even though the problem's only asking us to find phosphate. So I'm going to write this down that I've got 0.014 moles left. So I've got 0.014 moles of this. What is my total volume in this reaction? Well, I added 50 milliliters of this to 50 milliliters of this, so my total is 100 milliliters. So my total volume total is 100 milliliters. Okay? I've got 0.014 moles of this left. Now notice, I've got this 2 up here. That is not going to come into play in this part at all. That only came into play when I was figuring out the difference between this one and this one. It does not come into play. Once I'm looking at the number of moles I have of this, I'm now zoomed in let's use a different color. I'm now zoomed in just on this part right here. So I've zoomed in here, so none of this other stuff matters. None of this matters at all. All right? This is going to be the only source of those phosphate ions. So I've got 100 milliliters, and how many moles do I have? I've got 0.014 moles. So moles, 0.014. In order to find my concentration, I'm going to take my moles divided by my volume. So my concentration, let's use a capital M for that, is going to be 0.014 divided by, and now I need to use liters again, so move my decimal place from here, 1, 2, 3, so divided by 0.1. So that's going to give me 0.14 molar. So the total concentration of Na3PO4 is 0.14 molar. And I'm going to look at those 3 concentrations again. So I've got the concentration. Remember, this is how we write it when we want to say we've got the concentration of something. Equals, this is going to be my moles divided by my volume. So this is going to be that 0.014 moles divided by my 0.1 liters. So again, that's my 0.14 molar. Now my concentration of PO4 anions is going to be equal to this times the molar ratio between PO4 and Na3PO4. So I'm going to start with my 0.014 moles Na3PO4. So it's like we're doing a little mini stoichiometry. Times, for every 1 mole Na3PO4, I have 1 mole of PO4 3 minus. And then again, we need to put that on top of the liters, on top of the volume. So we're going to multiply it by 1 over 0.1 liters. And that'll give me the molarity of my PO4 anions. Can't even see that. My bad. So that's going to be 0.014 times 1 over 1 divided by 0.1. That's going to be 0.14 molar again. Finally, concentration, Na plus. So again, we're going to start with our 0.014 moles Na3PO4. And 1 mole Na3PO4 is 3 moles Na plus. Because there's 3 sodiums in each of these, I'm going to have 3 moles of sodium. And times that 1 over 0.1 liters. What'll that get me? It's going to take 0.014 times 3 divided by 0.1. That gets me 0.42.